In the paper, Random Order Interval Selection, authors Allan Borodin and Christodoulos Karavasilis introduce a novel approach to the interval selection problem in the context of online algorithms. The interval selection problem is a fundamental problem in computer science, where the goal is to select an optimal interval from a given set of intervals based on certain criteria. In this paper, the authors focus on the online version of this problem, where intervals are presented one at a time, and the algorithm must make an irrevocable decision about whether to select or reject each interval without knowing the future intervals. The proposed algorithm uses a random order strategy, meaning that the intervals are presented in a random order. This strategy allows the algorithm to achieve better performance compared to deterministic strategies. The authors provide a detailed analysis of the algorithm's performance, including its competitive ratio and the expected number of selected intervals. One of the key contributions of this paper is the development of a new lower bound for the competitive ratio of any online algorithm for the interval selection problem. This lower bound is used to show that the proposed random order interval selection algorithm is nearly optimal. The paper also discusses several variations of the interval selection problem, including the case where the intervals have different lengths and the case where there are multiple types of intervals. For these variations, the authors provide modified versions of the random order interval selection algorithm and analyze their performance. In conclusion, the paper by Borodin and Karavasilis presents a significant contribution to the field of online algorithms by introducing a novel approach to the interval selection problem. The proposed random order interval selection algorithm achieves near optimal performance and provides new insights into the nature of online algorithms. In the realm of online algorithms, the optimal deterministic algorithm for unweighted interval selection with revoking is 2k competitive, where k represents the number of different interval lengths. This paper delves into this problem under random order arrivals, a model used for beyond worst case analysis that also captures stochastic I.D. settings. The authors demonstrate that the simple greedy algorithm, which is optimal and 2k competitive in the adversarial case, is 2.5 competitive in the random order model, removing the dependence on k. The paper also discusses the application of interval scheduling in various fields such as routing, computer wiring, project selections during space missions, and satellite photography. It provides an overview of related work in the field, including studies by Lipton and Tompkins, Faigle and Nawijn, Woginger, Canetti and Irani, Fung et al., Bachmann et al., Borodin and Karavasilis, Emick et al., Garay et al., and Im and Wang. The paper highlights the importance of understanding the power of randomized algorithms with adversarial arrival order compared to deterministic algorithms with random arrivals. It demonstrates how to take advantage of the randomness in the arrival order to extract a random bit with bounded bias. This research contributes to the ongoing efforts to improve our understanding of online algorithms and their applications in various domains. In the context of interval scheduling, this paper discusses the competitive ratio of algorithms under random order arrivals. The authors consider a simple greedy algorithm that is 2k competitive in the adversarial on-order setting and extend the 1 competitive algorithm from the real-time setting. They provide an upper bound of 2.5 on the competitive ratio for this algorithm under uniformly random arrivals, using a charging argument motivated by Borodin and Karavasilis, 2. Additionally, they give a lower bound of 1/2 on the competitive ratio of all deterministic algorithms with revoking under random arrivals. The paper also explores the extraction of random bits with worst-case bias of 2/3 when there are at least 2 distinct item types, utilizing the random arrival of online items. This technique can be applied to other classify and randomly select algorithms that choose between 2 classes of items, when revoking is allowed. Furthermore, the authors consider a setting where there exists a global ordering amongst all input items, allowing for unbiased bits to be extracted throughout the execution of the algorithm. Under this assumption, they give a 6 competitive algorithm in the case of 2 different interval lengths and arbitrary weights. The paper is organized into sections, starting with definitions and a description of how the mapping from optimal intervals to intervals accepted by the algorithm is defined. The main analysis of the algorithm in the random order model is presented in section 3, where the authors deal with the case of 2 interval lengths and later extend it to any k greater than 2. Section 4 presents two different processes to extract random bits using random order arrivals, which are used to de-randomize a one-randomized algorithm for the case of single-length arbitrary weights intervals. The paper concludes with some open problems and future directions. In the random order model, interval scheduling is a complex task. The authors of this research paper introduce two types of conflicts: partial conflicts and containment, or inclusion, as shown in Figure 1. To evaluate the performance of an online algorithm, they use the concept of competitive ratio, aiming for a competitive ratio close to 1. They also describe a charging argument method for analyzing the algorithm's performance. This method involves mapping optimal intervals to those taken by the algorithm, either directly upon arrival or through transfer when an interval is replaced. The charging function, phi, is defined to represent the total amount of charge to any interval in the algorithm solution, which can be broken down into transfer charge and direct charge components. The paper highlights the flexibility provided by choosing different optimal solutions for a given sequence, which facilitates the proofs and could be beneficial in tackling other problems in the random order model, particularly when revoking is allowed. Overall, this section provides a detailed analysis of the challenges and methodologies in optimizing interval scheduling algorithms under the random order model. In the context of the random order model, this research paper section delves into the competitive ratio of an algorithm for solving interval selection problems. By employing Wald's inequality and leveraging the fact that the sum of charges for all intervals in the algorithm's final solution equals the optimal solution value, the authors establish a bound on the competitive ratio. They introduce the concept of a predecessor trace, a list of intervals that were once accepted by the algorithm but later replaced, akin to Woginger's predecessor chain in the real-time model. The paper then analyzes the performance of algorithm 1, a greedy algorithm that always accepts non-conflicting intervals and replaces existing intervals only if they are entirely subsumed by new intervals. The authors note that any interval taken by this algorithm can be directly charged by at most two optimal intervals due to partial conflicts. This leads to an upper bound of 2 on the competitive ratio for single-length instances. A lower bound of 2n, n plus 1, is also provided through an example instance where algorithm 1 is 2n, n plus 1, competitive. Overall, this section of the paper focuses on the theoretical analysis of algorithm 1's performance in the random order model, providing insights into its competitive ratio and the role of predecessor traces in understanding the algorithm's behavior. The paper presents an algorithm for solving the interval scheduling problem with transfer charges, focusing on instances where there are only two different lengths of intervals, denoted as L and R. The optimal solution consists of intervals IL element of L, IR element of R, and some intervals is subset equal S, where S is a set of small intervals entirely contained in the large intervals of M. The algorithm aims to choose the optimal solution that contains the latest arriving IL element of land IR element of R. A key lemma in the paper states that for any instance with a structure as depicted in Figure 3, we have that E, phi, I element of alg, is less than or equal to 2.5. This is proven by bounding E, Tc, I, where Tc1 denotes the event that a transfer charge of 1 occurs, and Tc2 denotes the event that a transfer charge of 2 occurs. The paper shows that the probability of Tc1 is at most 1/2, and the probability of Tc2 is at most 1/4, resulting in E, Tc, I, is less than or equal to 1.5. Since Dc, I, is less than or equal to 2 for all I, we have that E, phi, I element of alg, equals E, Tc, I, plus E, Dc, I, is less than or equal to 1.5 plus 2 equals 3.5. In the computation of expected transfer charge, we consider two distinct cases, Tc1 and Tc2. Tc2 is more complex, involving drawing without replacement. The probability for Tc2 is calculated as a ratio of factorials, with the numerator being the product of factorials of L plus R and S, and the denominator being the factorial of L plus R plus S. For Tc1, the scenario involves an interval from M arriving first, followed by either all intervals from L or R, then the first interval from S, and finally the last interval from the other set. The probability for this case is computed using conditional probabilities, specifically PR, BR, AL, and PR, AL. which are also expressed as ratios of factorials. The final expression for PR, AL intersection BR, is derived by multiplying these two probabilities together.